So good morning, everybody. I would like to thank the organizer for doing this humongous task of gathering such a, all people of science mechanics in the country. So what I shall be talking about is the properties of liquids in an asymmetric confinement. I'd like to acknowledge Edwin Tendong, who did this work as a part of his PhD program, and my collaborator, Professor Tanusi Shahadas Gupta. So let me straight away go to the theme. So, fluid in a symmetric confinement is something pretty well studied. Like, the effect of confinement has been bothering, people for a long, long time. Now, what I mean by symmetric is that if you consider suppose you take two walls and a fluid inside, if the interaction between the fluid and particles of the intervening fluid is the same for both ends, then it's a symmetric confinement. And asymmetric confinement obviously will say that the interaction between the fluid and the walls are not the same at the two ends. Now, why bother about that? Because nowadays, a lot of device application are done based on so-called heterostructures. That means the walls on the two ends are different so far the properties of different properties like as for example electrical property, polarity, etc., or the tendency of wetting, etc., are different. I like those devices are essentially like stack of different kind of structures. The stacking could be stabilized by many different means, like van der Waals stacking is possible, and so forth. Now, those stacked materials are very important for many applications, including, let's say, energy storage devices, in the separation technology, and so forth. There's a lots and lots of things. Now, for all those applications, and not only for the application, but also fabrication, like the fabrication of heterostructures are done typically in a solution phase. Now, how the fluid of the solution is going to behave within these two walls of different natures affects the stability and so forth. So as a result, to understand how a fluid behaves when the two walls are different, so where the interaction with the intervening fluid is concerned, is certainly important. And this has not received a lot of attention in the literature, although the electronic property of such stacked material has been, a system of a lot of investigation in past few years. So in order to sort of bridge this gap, how to understand what a fluid behaves in asymmetric confinement, we have carried out this study where we basically, this is a sketch of the system that we have studied. So let's say there are two reservoirs. So there's a reservoir at a given chemical potential, and then you insert two walls. One wall weakly attracts the particles, and the other wall strongly attracts the particles. So as a result, it's asymmetry between the two walls. The interaction between the wall particle interaction is given by standard so-called 9-3 Lennard-Jones potential, which is like integrating the over the wall particles. So you don't really consider the structure of the wall explicitly. And the particle in the wall are taken to be Lennard-Jones. Now, the two important parameters that we shall be considering is the separation between the two walls, which we denote by H, and we take H to be a few times the particle diameter of the fluids. So it's a strong confinement limit that we are considering. So if you take particles of the order of 10 to 20 nanometers, then confinement will be typically between 10 to 100 nanometers. And then the other thing is, of course, important is the asymmetry of the interaction. The asymmetry is denoted by epsilon S by epsilon W, where epsilon W is the Lennard-Jones parameter, energy parameter for the weak wall, and S is that for the strong wall. We consider epsilon W and epsilon F equal to 1 in the entire study, and we vary epsilon S to change the asymmetry. Well, here is a panel where we just show how we do the calculations, which is certainly not so important for audience here. All I can say, the structural property has been studied by using standard grand canonical Monte Carlo simulation. And then the dynamical property has been studied by using standard molecular dynamics NV simulation by taking some random configurations chosen out of the grand canonical Monte Carlo simulations. So first, the structure is some property is shown here. So what we do here, we calculate the number density of the fluid particles within the confinement while we change the asymmetry and the slit width. So what we find that there is okay. Now what we plot here is the rho by rho zero ratio, where rho zero corresponds to the bulk system that we have taken, where the bulk refers to the reservoir. The reservoir parameters are taken to be in the fluid region, not too far from the fluid-solid phase coexistence. Now, what we find that there is a change. See, average rho by rho zero less than 1 means the density of fluid within the pore is lower. It's a rarefication of the medium. And then it goes above 1 is a denser system where essentially you get capillary condensation. So this is capillary condensation part and the capillary evaporation part. And of course, the system like this, because there's a wall, you get layers, and the structure of the layers are being characterized by using this kind of parameters. And then the phase diagrams looks like this. You go from fluid, and then you get a dense fluid, and then the structural parameter given the bond order parameter is showing crystalline order, and that happens as you increase the layer size, depending on the commensurability of the length with the walls, you get with the layers, you get multiple layers in the system. Next, what we calculate is the viscoelastic property of those systems as we cross the boundaries of the. So basically, there are two boundaries you can think of. One boundary is from rarer fluid to denser fluid, and then the fluid itself shows a change from, let's say, fluid structure to crystal structure. Okay, now viscoelastic response has been computed by computing the stress autocorrelation function given by CET. So basically, we calculate stress tensor, and then we compute the autocorrelation of the stress tensor, then take a Fourier transform of that. That essentially gives us the Fourier mode of the stress autocorrelation function, wherefrom we compute the loss and storage modulus by using the real part and the imaginary part. The storage modulus tells the elastic property, and the loss modulus tells about the viscous property. A typical case looks like this. So essentially what happens, depending of course on the parameters like H and Xi, you get a crossover between the storage modulus and loss modulus, and the crossover point actually depends on the system details like H and Xi, and this crossover point essentially defines the frequency of the viscoelastic relaxation. So what happens that for high time, that is low frequency, the system is viscous, and on the other end is like behaves like elastic because the storage modulus exceeds the loss modulus.
2 minutes.
Okay, and so this is how we define, an inverse of that frequency gives you the viscoelastic relaxation time scale. So now, what we find that if we compute the viscoelastic, essentially the viscoelastic relaxation time, the relaxation time for low asymmetry actually, shows gradual change, and then as we increase the anisotropy beyond some critical anisotropy, it shows a jump. It increases very rapidly. And if you take this jump point and plot, okay, you also calculate something I should have told. We also calculate the structural relaxation by using the intermediate scattering function, by defining that the elastic module, the scattering function drops to 1 upon E. So that gives a typical relaxation time, structural relaxation time, and they almost coincide. That structural relaxation time, so that coincides with the fluid rare to denser, fluid boundary, as well as this relaxation time that we measure from the viscosity and also the structural from the intermediate scattering function. Now, as I said, remember that the viscoelastic relaxation time actually increases rapidly beyond certain value of the critical value of the asymmetry and that depends on H, and the behavior is shown here in this graph. What happens that for low values of, okay, what we compute here, show here is the difference with respect to the point where it where shows the change from, let's say, rarer to denser medium, and there's two regimes. In one regime, all the data for different H appears to be almost independent of H, But then in the rapid growth, of course, there's a dependence on age. The way, okay, so 10 minutes done, right? Okay, so now briefly the physics is that as you go to low elastic module limit, then the system actually is having layers that are weakly coupled layers. As a result, the system actually behaves in a very similar way so far as the relaxation is concerned. But as you increase the asymmetry, the layers becomes more pinned to the wall and they slow down. And this slowing down contributes to the rapid increase. And of course, because there's a it's not universal because different layers actually behave in a different way. Finally, if you go to close to the case where you encounter the layer going from fluid to solid, we see a situation where it's a gel-like behavior, where the storage and rest modulus actually almost overlaps. So let me summarize saying that what we have found that there are a couple of transitions from rarer to denser medium, and then the fluid to solid transition which happens in the layers themselves as you change the asymmetry. And then there's different regimes of viscous relaxation, a part where it's a universal, like it doesn't really depend on slit width, and that is driven by weakly absorbed layers, and a regime where you get a steady growth, a steep growth, and that is essentially contributed by strongly pinned layers. And then fluid to solid transition actually shows the intermediate gel-like behavior. So I thank you a lot, and these are the people. And Edwin did this work. He is now back to his country with a job there. He was from Cameroon on TWAS Boss Fellowship. So thank you very much.